Thank you for being here today. We are Vision UAV, and this is our final design review. My name is Caitlin Schroll. I'm the design team lead for the team, and I'll go ahead and introduce you to the rest of the team. We have Ryan Hom, Cassie Freeman, Yara DeSefa, Matthew Simpson, Kayla Romero, May McGinde, Raymond Wang, and Bjorn Basenden. This is just an overview of our presentation, what we will be talking to you today about. We will go through an introduction. We'll talk about our wind tunnel results and the weight and balance of our subscale UAV. We'll go into the material verification testing. We'll talk about the structural analysis that was completed, and then we'll go into our avionics design and integration, and then finally we will go through our manufacturing and our flight test. The objective of this presentation is to familiarize you with what we did last semester and how our predictions met the requirements, and then how we transitioned into the detailed design semester. And we will demonstrate the airworthiness of our subscale, and then we will be seeking approval to move into the full-scale manufacturing phase. Vision UAV was approached by El Paso Natural Gas Company, who was looking for an unmanned alternative method to surveying pipelines that ran from El Paso, Texas to Tucson, Arizona. The surveillance with the manned aircraft was getting too expensive for this company, so they wanted a different solution. Vision UAV came up with a concept where the UAV would take off from El Paso, Texas, and it would be piloted remotely until cruise. In cruise, it would be autonomous, and it would be flying different routes over the pipelines and be looking for any kind of cracks or anything wrong with the pipelines or illegal tapping. Once it got into the area of Tucson, Arizona, it would then be taken over manually and piloted to land in Tucson, Arizona. El Paso Natural Gas Company gave our team certain requirements that needed to be met for this UAV. They wanted no more than a 55-pound UAV. They needed their UAV to be capable of 300 miles, and it needed to be reaching 300 miles, and it needed to have an endurance of 6 hours. The takeoff and landing distance needed to be no more than 500 feet, and the cruising airspeed had to be a minimum of 70 knots. Finally, the UAV needed to be capable of a 2.5 G turn. We came up with our design, and the predicted aircraft values from our preliminary design semester for the full scale were that our aircraft was 43 pounds, it had a range of 337 miles, and a max endurance of 8.1 hours. The takeoff and landing distances were 183 feet and 104 feet respectively. The maximum cruising airspeed was 101 knots, and it was capable of that 2.5 G turn. So because the preliminary semester was predicted to meet all of the requirements, we moved into the detailed design semester. And immediately, we realized that because of manufacturing space limitations, we needed to subscale our design. So this subscale design, Scout, is half of the preliminary design rate, and it maintains the aspect ratio and wing loading from the preliminary design. Different requirements were given to us for the subscale design. The weight needed to be half of the original value, which gave us a range of 19.4 to 23.7 pounds with plus or minus a 10% margin. The aspect ratio stayed the same at 10.85, and the power loading and wing loading also stayed the same, plus or minus 10% of that value. The takeoff and landing distance changed because the subscale prototype would be flying at the Chino Valley RC airfield. So that landing distance and takeoff distance was now 800 feet. There were some other design limitations that we realized. The operating altitude needed to be less than 400 feet above ground level, and we would not be flying our UAV at more than 10 knots. Finally, the maneuvering load that our UAV would be capable of is 4.5 Gs. All of these requirements would be able to be verified through testing, analysis, or inspection. This is a preview of our subscale design Scout. This is the actual picture, as you can see. It utilizes a high-mounted wing where the fuselage and payload sit underneath. We have a tail dragger configuration and a conventional tail. We also utilize twin pusher motors and retractable landing gear, and then that main wing is a NACA 1412 airfoil. I'm going to go ahead and pass it off to Ryan Hahn and Cassie, who will be talking about our wind tunnel testing results.
Thank you, Caitlin. So before manufacturing our subscale, Vision UAV conducted a wind tunnel test in order to verify our predictions from our initial design. The model itself was 1/15 the size of the initial design and had a tail-on, tail-off configuration. The test was conducted in a closed-circuit wind tunnel in the Tracy Dorland Wind Tunnel Lab. The test condition, the test was run at 25 meters per second, producing a Reynolds number of 68,000. This is significantly lower than our predicted Reynolds number of the initial design, the effects of which I will discuss later. The model was tested for roll, pitch, and directional coefficients at angles of attack from -4 degrees to 12 degrees, and we also applied a side slip angle from 0 to 10 degrees. And in the image shown is our flow visualization that we use to see areas of laminar and turbulent flow. This is our lift curve slope that was produced from the test. Our predicted stall angle of attack was 9 degrees. Compared to our initial prediction for the subscale, which was 18 degrees, this large difference was due to the much larger Reynolds number from our prediction, which was around 610,000. We have a -0 lift angle of attack. This is good because our cruise is going to occur at a positive angle of attack. And you'll also notice that the difference between our tail on and tail off configurations was very small. This shows that our tail does not have that large effect on the lift that we need in order to remain in flight. Next is our longitudinal static stability. This curve we would like to see a negative slope, and as you can see we do meet that requirement in both the tail on and tail off configurations. We also collected data on our lateral static stability, in which we would also like to see a negative slope. In this case, at all 3 different angles of attack at 0, at our cruise angle of attack, and at 10 degrees, we do not meet this requirement. Therefore, it was determined that our model was unstable laterally. Next, finally, our directional static stability. In this case, we do want to see a positive slope, and same as last time, at all 3 different angles of attack, we are unstable. And so, because of these failures in lateral and directional stability, we looked over our wind tunnel model, and we did notice that our horizontal tail was off-center slightly, which may have skewed some of this data, along with the lower Reynolds number that we were testing at. And so Cassie Freeman will now discuss our design changes based off of the wind tunnel results.
All right, after completing wind tunnel testing, Vision UAV decided to implement 2 design changes. The first design change can be seen behind me, where we decided to increase the size of the horizontal and vertical tail by 25%. This will increase our stability. The second design change was to raise the location of the empennage to be level with the fuselage. During wind tunnel testing, we saw very little flow over our tail, which Ryan pointed out in our lift curve slope. It really didn't have much of an effect on our lift, so we decided to raise the tail so that there was sufficient flow over the tail during flight. The new subscale design can be seen behind me. We have a neck of 14-12 airfoil with a 9-foot wingspan. The overall length of the aircraft is 5¼ feet. The overall height is 1.7 feet. The span of the vertical tail is 0.69 feet, and the span of the horizontal tail is 2.5 feet. I'm going to pass it off to Yara in a second. We'll go over our updated stability.
Using the published manufactured values for weight components, we started calculating our center of gravity for scale. We started using the individual CG locations of each component. For components that weren't fabricated yet, we used weight per volume ratios. And at its most forward location, the landing gear is deployed. At its most aft location, the landing gear is retracted. using the predicted CG location X bar and the geometric X bar of our aerodynamic center, we were able to calculate a static margin of 0.23. Accounting for both the increase in our horizontal and vertical stabilizers and an updated center of gravity, we calculated that our aircraft would be stable based on the longitudinal, lateral, and directional stability derivatives. And now I'll pass it off to Matthew Simpson, who'll talk about our material verification testing.
Okay. So for the material testing that we performed this semester, we started off with composite skin tension testing. For this, we had 4 different configurations we were testing, and we tested 5 samples per configuration. In addition, we did composite skin bolt tear-out testing, again, to make sure that we would have safe margins for the bolts that would be connecting the wing to the fuselage. And then finally, we did control surface hinge testing to ensure that our control surfaces would be able to withstand the aerodynamic loads they would see in flight. So starting off with our composite skin tension testing, we noticed that having the outer layer in the 45-degree direction helps resist failure due to torsion and shear. And so going with this, in addition to taking the average ultimate tensile strength across those, or using those 5 samples from each of the 4 configurations, we determined that the 4th lathe configuration, which was the 45-degree on the outside and 0-degree on the inside, gave us the highest average ultimate tensile strength, which we determined would be safe for use on our monocoque fuselage. Moving on to the bolt tear-out testing, we did show in testing that the first mode of failure for the lathe configuration chosen previously would be tear-out, and so doing the testing, we loaded it to 2,000 pounds and noticed that the holes only extended 3/16 of an inch, and we determined this would be safe for use on our fuselage, as we would not be seeing those loads in actual flight. Finally, our control surface hinge testing. Each hinge needed to, or was required to withstand 4 pounds in flight load. Our first hinge was loaded to 22 pounds in 2.2 pound increments and did so without failure. We then took our second hinge and loaded it in 1 step to 22 pounds and again saw no failure and verified that these would be safe for use on our control surfaces. Next, I will pass it off to Kayla Romero, May McGinday, and Raymond Wang, who will go over our structural analysis.
Here we have our maneuvering band diagram, also known as a flight envelope. This will pretty much tells us where we will be able to fly our subscale UAV Scout. In the red shows where structural damage will occur, and beyond that is where structural failure will occur. So some of our speeds are the stall speed, which is 23 knots, our corner speed, which is 49 knots, our cruise velocity, 56 knots, and the dive speed not to exceed is 78 knots. Next, we have our combined band diagram with gust lines to determine if any wind effects will affect our maneuvering for our subscale UAV Scout. As you can see, wind does not affect our maneuvering. Next, we will go to the components of our wing. So right here we have our spars, which are balsa wood, and then we have 1 layer of carbon fiber, which is 090, and inside of the wing is a foam core as well as a carbon fiber wing spar. Then we have our nacelles right here, which are also balsa wood, and then our wing mount, which is ABS plastic, and it is attached with bolts and flying nuts. Next, I'll pass it off to May McGinday. She will continue with our structural analysis.
So finite element analysis was conducted on our subscale wing to examine deformation and stress before a structural test was completed on a fully fabricated wing. Once the material properties were applied and defined, a fixed support was applied to the bottom of the external mount with the fuselage constraints, and the distributed lift force was applied on the bottom side of the wing with a magnitude of 121 pounds. This force was obtained by multiplying our max weight of 21.5 by the factor of safety of 1.25 and the load factor of 4.5 Gs. So structural deformation was then obtained from the ANSYS. The figures on the left are the deformations in ANSYS, and they're exaggerated 75 times its true scale to see how deformation occurs. The maximum deformation occurs at the wingtip with a magnitude of 0.5 inches. Once the wing was fully fabricated, the wing was flipped upside down and mounted at half the span onto a table due to symmetry, and sandbags were added onto the bottom side of the wing in increments of 2 pounds to measure deformation, and a max deformation of 3.2 inches was obtained. This was expected for the structural test to have larger deformation than that of ANSYS because the physical test takes into consideration the interactions of the parts of the individual components, whereas ANSYS is more difficult, much more difficult to accurately model those parts, and so we have much larger deformation. So then the graph shows the maximum equivalent stress, and it occurs on the wing skin right where the wing spar ends, and it was compared to the ultimate tensile and ultimate compressive strengths of carbon fiber composite at 90 and 0 degrees, and margins of safety for tensile and compressive were obtained to be 21.2 and 20.1 respectively. I understand that the margins of safety were significantly larger, and so Vision UV concluded that the wing would not fail. The wing skin, I beg your pardon. So shear and tensile analysis were conducted on the wing, motor, and main landing gears fasten joints. All joints exhibit excess strength as what would be experienced in flight, compared to what would be experienced in flight. Three independent blocking methods were chosen for each fasten joint. As you can see, the wing, motor, and main landing gear all have the same 3 blocking mechanisms, whereas the tail has the 3rd blocking mechanism of an eye lock nut, and this was chosen for manufacturing constraints. I'll now hand it off to Raymond to discuss avionics integration.
Hi, my name is Raymond Wang, and I'll go over the avionics design and integrations. So as shown on the diagram, this is the avionics layout for the UAV, and the power conditioning units powers the receivers and all the servos with the proper power, while the battery powers the power conditioning unit along with the engine. The high-tech Optimal 9 receiver and an ERAU-9 X transmitter was used for the communication between the pilot and the UAV. A total of 4 servos were used on the UAV. 2 were embedded inside the main wing, 1 inside the vertical tail, 1 inside the horizontal tail. And the servos were used to actuate the control surfaces. A power lithium polymer battery, 2 lithium polymer batteries were used, along with a power conditioning unit, and a 2 E-Flight Power 25 motors were used for the power system selection. This is the inboard profile. As you can see, the inboard profile consists of the GoPro, 2 ballasts, 2 batteries, 1 receiver, a power conditioning unit, and an electronic track controller. These are all mounted onto the payload sled for ease of access. Next, I'll pass it off to Bjorn, who will talk over the manufacturing.
I'm going to quickly go, well, not very quickly, go over what we did to actually build this aircraft. There's actually a few different designs and types of construction used. The very first thing we did was lay out the fuselage. We created a polystyrene foam mandrel by laminating layers of 1-inch thick foam. We then hot wired that out into a 7-inch diameter circle, and then laid, you can see the release paper here, and that was to allow us, after the 4 layers of carbon fiber had cured, to slide that mandrel out so that we would have this, this is a monocoque fuselage. There's actually no internal strength in there, there's no ribs or stringers, it's just the carbon tube. Next, we did the horizontal and vertical tail. These were used, constructed in a similar fashion, using the laminated 1-inch polystyrene foam. They were then hot wired out to the profile, and then the carbon was laid up directly over them. So the foam core in the wing and the horizontal and vertical stabilizer is actually captured in there, and it was not removed after fabrication. before, you can see the wires coming out of it. Before we did the layup, servos were embedded for control of all the control surfaces. And they were just glued in place, and the carbon was then wrapped around them. Next, we had to construct our control surfaces. These are balsa wood stock that have been cut down to size and then coated in a monocoat covering, which adds strength as well as protects them from damage because balsa is very soft. We then added the hinges that Matt explained about hinge testing to each surface, as well as the control horn, which will allow us to actuate the control surface. Here's an image of the tail boom and stabilizer. Tail boom, horizontal stabilizer, and vertical stabilizer, all mocked up, ready to be assembled. This is what they will look like, as you can see, in final assembly. We then fabricated the wing. Here you can see the layout when we were figuring out sizing. The wing is actually built in 6 sections, so it's the same polystyrene laminated construction. Each 1.5 foot section was then hot wired out. The sections were then slid onto the main spar and glued in place. Here you can see one of those hot wired sections. This is the center section between our 2 nacelles. In this image, we're embedding all of our electronic wiring in the wing. We actually cut slots into the wing, laid the wiring, and then as you can see in this picture, we covered all those wires to protect them from the carbon covering. You can see in the corner here, that's one of the servos that was embedded. All the wires are running actually right behind the spar, and everything was held in place to be covered. Here you can see the wing being laid up. The wing is a single layer of 90-0 carbon fiber layup, and it is actually one continuous piece, so there's no points in it for the word stress concentrations along the wing. Here's the final step of integration, is mounting the wing to the fuselage. They're 2 very contrasting shapes, so obviously you can't just bolt them together. The mount in the middle here, you can see, was CAD modeled and then 3D printed. The shape accepts the bottom of our NACA 1412 airfoil, as well as the top of our 7-inch diameter fuselage, and allows them to be bolted together with the 4 through bolts to hold its security. Here's the final assembly. Here's the final assembly. In here, you can see the wheels are retracted. And I think, do we want to retract them real quick? I think we have time. We'll show you guys real quick the retracting landing gear. It's kind of like the party piece of the airplane.
The motors aren't going to turn, are they, Bjorn?
No. Yep. Okay, so there we go. So you can see right now the gear's down, and then it retracts into the raised configuration. You guys see it over here, and then back down. All right. Next we have, I'm going to go over our flight test results. We flew this airplane last Tuesday at the Chino Valley Airfield. Huh? This Tuesday? This Tuesday.
Seems like a lot longer.
Seems like the flight test, the conditions were great. We had almost no wind. It was a slight breeze blowing right down the runway. It's kind of hard to beat. Let's see, I think I have to, I don't have to click on the video yet. Here's our main speeds. We had the Chino Valley Police Department out there with us, radar gunning. So right at rotation, as we're taking off, we got a record recording of 36 knots. We did a flyby at our cruise configuration with the landing gear up of about 53 knots. And landing right before touchdown, they got us clocked at 33 knots. Here you can see again the landing gear down configuration, as well as the landing gear up configuration. I apologize if this is really loud. I don't know what the last team in here was. There might not be any noise at all. Maybe. So you can see right now the video is really bumpy. That's because we're still on the ground. The camera is actually on a stabilized mount. Yep, you'll see it goes smooth there. Oh, there is. So the camera is actually sitting on a 3-axis gimbal. It holds the camera level through all phases of flight. One of our recommendations to future teams is to leave the protective coating on your nose bowl until you're ready to fly. There's some stuff on it. Here you can see us running through all of our different flight tests. We start out with just simple circles around the airfield, getting a feel for the aircraft, getting it trimmed out, kind of seeing how it's happy to fly. This is, I believe, 3 times acceleration. We're then going to go into a couple maneuvers. We do some figure 8s in order to get the aircraft to a high bank angle to test the wing loading as well as the full maneuverability of the aircraft. We're then going to one more circle, I think. The aircraft actually flew very nice. It was super straight. It required very little trim. We were surprised. We oversized all of our control surfaces because we're not obviously professional manufacturing with jigs and molds and stuff, so we were worried if anything was twisted. We actually wanted to be sure we could overcome any of that inconsistencies in the build. So the control surfaces on this aircraft are actually much larger than our design originally. Here we're doing a practice approach. You can see coming through, getting used to how the aircraft slows down, how much time it takes to decelerate, and then at about the halfway mark on the runway, we did a go-around to come back for a real landing. Yeah, sorry, apologize for the nose bowl. Here we go. This is coming downwind here. Is there? I hear some. Maybe is there noise? I don't know if I'm adjusting the volume or something else now. Coming around. This is where we're slowing down, bringing the power way back. You'll see there's kind of a dip there, and then there's another one right over the end of the runway where we come back to 0 throttle. Right about there. Nice flare, and successfully back to the ground. Everyone was pretty excited. So, like I said, the airplane flew very straight. I was the pilot of the aircraft. We were very surprised. It took about just over a degree of nose down trim and about 2 degrees of right aileron trim, which for an airplane of our build skill, I'll be not afraid to boast on that one. I was pretty proud of us for requiring that little bottom amount of trim. There's the airplane. You can kind of see the gimbal sitting up there. I don't know how long-winded this is. I wasn't excited at all.
I've never seen that much of a smile.
Did you retract your gear?
In flight, yes, we did. We did, after takeoff, we did 2 circles to trim the aircraft out. We then retracted the gear and then went into, I believe in our appendices, we have flight test cards. We actually had a list of maneuvers that we were running it through with the figure 8s and circles, as well as climbs and descents. Oh, let's not do that. There we go. Now I'm going to pass it back to Caitlin for the review of the overview of the project.
So going back to our subscale design requirements, going through this detailed design process, our weight ended up being 21.5 pounds, which was in that range of the half weight requirement. Our aspect ratio did stay the same at 10.85, and our power loading and wing loading were within the ranges that we set out and had required of ourselves. And then finally, that landing distance, looking at flight test data and looking at that video, we determined it was approximately 350 feet that we landed. So that is also within the requirement of 800 feet. So looking at these requirements and looking at the testing that we did, the analysis, our team says that we are determined that we have met all of the requirements for this semester. Throughout the semester, we thought about a couple different risks that could possibly happen to our project. Some of these risks were that the wing layout could cure improperly. We thought about that part suppliers may not be timely or that materials may not be unavailable. We projected possibly a negative static margin after wind tunnel testing. We also thought about how our components could be damaged during integration, and then we also considered flight delays due to weather. So after this risk assessment was done, we actually talked about a risk mitigation plan. So a lot of that mitigation was put into our program plan, and just delegating the amount of time, the extra time we had. And so one of these risks actually happened to us. One of our part suppliers was untimely, and we had to wait a couple weeks for our carbon fiber spar. But we were able to move some things ahead, or move that time around, and we were okay on our program plan.
There were also delays to weather.
That too. Right. So we have all been logging all of our hours for this semester. We have totaled 1,785 hours for all 9 of us for this detailed design semester. At the beginning of the semester, we had a predicted hours. So this is for every hour of class time, we predicted 2 hours dedicated to the project outside of class time. And as you can see, that's pretty good. We came in a little bit underneath at the end of the semester. All of the hours that we spent were clocked into 5 different categories, and this was just based on the type of work that was completed. The total cost of all of our labor hours was $153,600. The manufacturing budget that was given to us was $1,150. We were originally going to be able to meet that budget, but a design change was necessary, and that was moving from a retractable landing gear to a fixed landing gear. So we went ahead and got that permission to go with our retractable landing gear because that was a strong feature of our aircraft. And so our budget for manufacturing went to $1,413. After all the testing that has been completed for the semester, the analysis, our maiden flight test, our recommendation is that we move into the next phase of a full-scale prototype and manufacturing. We've learned a couple lessons going through this detailed design semester. The first one is that a taxi test needs to be completed separate of the flight testing. We learned this the hard way. We got out there, we thought we were going to be completing a flight test. It ended up just being a taxi test. The second one was that there needs to be triple the length of the service loops that you originally expect. And this is just for ease of integration. We had a problem with that, and we had to go back and move into some larger service loops. Something that really helped us that we recommend to other capstone teams is get your production plan done early in the semester, get your program plan done, set those dates out, and it will greatly help your semester move very smoothly. I think the flight test date 2 weeks before, we didn't have much to do. We were pretty much riding it smooth, and it was it was an easy. We had a few integration things, but other than that, we weren't short on time. And then finally, in our preliminary design semester, we had some good insight, and we designed a lot of our UAV knowing that we would manufacture it in the detailed design semester. So that really helped us out a lot too. We would like to thank all of these people for helping us with this project. We have had so much help, so much support, and we would not have been able to complete this all. And I would definitely like to thank you guys for all being here today and listening to us. And I'd especially like to thank my team, because this would not happen without all of you guys. So thank you very much.
Thanks for organizing this.
And that concludes our final presentation.
Okay, we're going to start with.
All right. Excellent job. You were very successful. Anything that lands with a taxi back to the pits is very successful. Can you talk a little bit more about the catch you made in the wind tunnel testing that taught you that you needed to raise the tail?
So we had that flow visualization. We essentially had pretty much string just all along the back here and then on the tail as well. So while we were running the test, we just did pretty much a dry run at just our usual angle of attack, -4 to 12. Pretty much throughout the whole thing, we noticed that there was nothing going on in the back there. And so, I mean, that's bad clearly, because we want to be able to maneuver with that tail.
You can see the if you want
Yeah.
to see the design change really clearly, you
Yeah.
can see our taper here to the top
Wow.
versus the cone
Still-
straight back.
Yeah, so that was one of the indicators. Also, while doing our static stability data, the trends were definitely strange. We had talked to a number of professors just trying to see like what the heck is going on. As I mentioned before, the fabrication of the model itself wasn't perfect. We kind of just threw together just during time crunch because we needed to get the test, then begin production, and so that may have been one of the things. It also may have been just the location of the tail itself from slide slip. We're not too sure. Given time, we probably would have remade the model and then run the test again, just to
Absolutely.
verify that this
you
is happening.
re-verify afterwards.
Yeah. So,
There's not a whole lot of time for rapid retesting when we have one semester.
yeah.
Oh, excellent job, that's all I had.
Thank you. Thank you.
Okay, overall, you guys, really professional team, you guys all look great, you know, you're super professional about it, you guys delivered your presentation flawlessly, I couldn't nitpick anything on that. One of the things that I really liked was you guys had a really minimalist design of your slide deck. It wasn't cluttered, you guys took a lot of data that could easily overwhelm even technical engineers and compressed it into something that was very easy to digest, even for a systems engineer like me. And your guys' design solution was extremely well explained. You had a lot of good visuals. One of my suggestions would be is when you guys did your design iteration, I would add a small section or talk about how the design updates would affect your requirements. So what requirements were these design changes drive? Like what requirements are driving the design change? I know you guys have like a flight profile. I know that's different than a ConOps. Just to make sure that people understand what the full purpose of the system is before diving into technical details, would just give a little bit more detail and kind of follow kind of like maybe a hybrid format between what the previous team, if you guys are here with the presentation, and what you guys had. But I did like how you guys showed the different altitudes for the flight and everything there. For a design consideration, so you guys chose to put your wires inside of the carbon fiber. Did you guys consider like long-term for maintenance, for something that's a fielded system, how that might affect costs? You know, you have a problem, you have to replace the entire carbon fiber wing.
So how we designed the internal wires, they are, hopefully none of them will ever break because they're mounted firmly in place.
Mhm.
And if we do have to replace a component, say out in the cell, we actually have connections on both ends. So there's a connection where the wing separates from the fuselage. There's also a connection in the nacelle. So obviously, if something was to go through the bottom of the wing and slice a wire, yeah, we'd have to replace the wire, but we'd also be replacing the wing. So as long as, so say if the ESC controlling the motor was to fail, there is a connection in here where we could just quick disconnect that and throw a new one in.
Okay, I mean, excellent job, guys. I'm, you know, from a Raytheon perspective, I'm looking at this thing and it looks just like our Coyote drone. It was shocking, and you know, looking at your guys' in-flight footage, it seriously looks like a Coyote drone.
But it costs $1 million or a million times less.
Yeah. Yeah. And you guys did that in 2 semesters, so congratulations to you guys.
Thank you.
Just professional team. And from someone that's been through prelim detail before here, yeah, it's amazing what you guys did.
Thank you, appreciate it.
What it's telling me is, you notice there's a lot less questions from everyone, which means you guys covered quite a bit. That's what you want to do. However, now there was just some little things as always. I always look at those. When you had the full scale requirements, you're missing the cost. I mean, you have everything as far as the engineering, but what does it cost? That's what customer. And I don't know if it was given to you, but that's going to be the huge one. It's going to be, I mean, you design this, it has to be at this price.
So for our full-scale design, we did have that total
Yeah,
cost.
just need to put one line there.
Yeah.
Okay.
Okay.
And that's it. It's like, yeah, you're presenting to engineers, but also potentially.
Right. Right.
customers.
The business side of it.
Somebody is going to be buying it, so I understand. I
Exactly.
understand.
That's how the bills get paid, and that's how salaries get paid.
Yeah.
As far as material verification testing, it's the same with the previous presenters. It's like, this is directed to Embry-Riddle. This might be a good time to link, analysis to test, so you get better properties for the FDA, because it's unclear exactly what you guys are using in the FDA for properties. It's good that you tested it, and this is like the build and break method, the low high low enough, so you didn't have to go through several iterations. But now's a good time that you can actually model test components, and then you can actually find out what's going in at that level. And the reason I say that is because on the finite element analysis, the deflections are way off, and that's that's significant.
Yeah, it was very far. One of the things we did notice when we were doing that cantilever test, how we had it mounted at the point of symmetry, we were actually getting flex off into our supposedly fixed side of the wing. So, given more time, we would probably figure out a different way, or maybe just load the entire wing.
Yeah. Well, back to that one. Yeah, you could have done it, but one more time, the numbers are way off.
Okay.
I mean, that's significant.
Yeah.
That's huge. I mean, it just is.
Yeah.
And another thing I would have liked to have seen would have been, I know it looks really complex to you guys, but the first thing I would have done was just pulled out one of the strength and material books, done an MCO right at the root, right? And then you could have estimated what the deflection would have been, and it probably would have been closer when you find it out. Right out, yeah.
I think we did do some again calculations.
You need to throw those in there.
Okay.
Especially when the numbers are that far off.
Yeah.
Just at least say, hey, we did a sample
Just how does it
check.
back out? Okay.
Right, because the one thing you don't want to see is like, here's what the computer said, and here's what it said.
Yeah.
And that's just bam. It gets you to that garbage out, and it kind of like throws all this out. It just does. And something that we have done in the past is, you don't need to model, like all the way down to the nitpicky details. And I'll just give you a quick example. When we do analysis of, let's say chassis that have 36 reports, and these things will go on aircraft, they'll go on satellites, they'll go on rockets, I mean everything. So they have all these nasty environments. I have seen companies in Intel, I'm not sure if anybody's ever tried this, but they've actually tried to model a circuit report at every level as far as traces and all that. End of the day, the only thing you really want is a deflection of that printed circuit board during launch, because you're trying to calculate whether or not the leads are going to fatigue on the stuff that's on there. So what we did was, instead of modeling the crap out of the board, we did a 3-point band on the board, got the average properties, there's your model, you're done. So things like that could be done on a wing fly. We have to have on that, but there's little things like that that go a long way, especially when you're that far off.
Yeah.
Other than that, I'm done scolding you.
Yeah. Thank you. Appreciate it.
Really excellent presentation, very clean, very professional. All the same stuff that these guys said. Really nice job. I just have a couple of quick questions. So kind of alluding to a little bit of what some of the other panel members said about when you found out from your wind tunnel model that you didn't have the desired performance. Did you go back to your original design after the design changes? And I think it's on slide 7 where you kind of brought up what your requirements were and then what your predicted aircraft values were. Do you go back and recalculate your predicted aircraft values given the design change? And were you still meeting your
Not for
requirements?
the full scale.
No, the full scale was all last semester. These are actually all of our predicted values from last semester. So all of the information we got from the design change went into the prototype. There wasn't a whole lot of backtrack.
Okay, so that would probably be an important thing to take a look at, because
Yeah, absolutely.
If you do a design change and then all of a sudden you don't meet a full scale requirement, then the whole idea of doing the prototype, right, kind of may go out the window,
Yeah.
right? So make sure that you're going back to the whole point of the whole effort, right, in building a prototype, a subscale prototype, is to validate that the full scale is going to work out, right? So
Absolutely.
if you need to rerun the numbers, just rerun the numbers for the full scale as well. I like the retractable landing gear. That adds quite a bit of complexity to your
Yes.
design. What was the calculus there in deciding to go with retractable landing gear? Why did you decide to do it and take on the added complexity?
Dude, it made you go, ooh, ah.
when we were kind of spitballing designs, we were looking for something, if you think about the Coyote or the In-Situ Scan Eagle or anything like that, all of them are kind of a tube with a wing. So we wanted to stick to that aerodynamic, efficient design, but our requirement was to take off and land from a parking lot. So we needed wheels. So our solution to that was retractables. You get the, do we have an in-flight picture? You get that, stick with a wing in-flight profile for excellent low drag and all the things. But yet when you're coming down the land, you can still you can still take off from our required airstrip.
So clearly that you take a drag hit with a fixed landing gear.
Yes.
Right? Did you calculate what that drag hit
We did.
is?
The first semester we did.
Oh, yeah.
Okay.
It was the difference of almost, what was it, like 40 minutes of flight.
Yeah,
Yeah.
I was gonna say, one of the driving things that made us go with that retractable landing gear was for that endurance and for that range. Those calculations really drove that design.
And that's something we could totally have in here. We mentioned that all last semester, and we understand you weren't here for that, so I get where the questions come from.
Yeah.
Okay.
That makes sense.
Yeah.
And then, did you guys write a test plan before you went flying?
We did.
Define what your test
You have
plan
she's got the slide. We wrote up test cards. Our chief engineer, Cassie, was standing next to me while we were flying, and so we did a run up on the ground from everything, checking control surface direction, checking securement of things. We did a full power test from no throttle to full throttle and back down. We then checked the rigidity of everything after that power test. We did 3 high-speed taxis, and that was mostly just for me to get used to the handling of the aircraft on the ground. And then once we got into flight, we had the circles. It's
a little hard to
shrunk,
read,
but then once we were in flight, is this phase 2? We had climbs, circles. We then had those higher bank angles to load the wing higher, and then coming in for landing.
Okay. Yeah, that's all really great, solid plan, and I think you talked through it as the video was going. My only add there is highlight in your presentation here what all your objectives for your flight tests were.
Okay. Okay.
And then, at the end, somehow summarize whether or not you met them or fell short in some areas. A summary of your flight test results would be.
Absolutely.
It's like requirements in each section and how you made it. Flight test.
Okay.
That's all I had. Great job.
Thank you. Appreciate it.
Really great stuff. I'm super excited to see it, especially when it goes well. And couple questions and a couple comments. Yeah, most definitely echoing what Eli just said. State your test objectives before every test, and also if you're going to show test results, then that would be helpful. Talk a little bit, or maybe can you talk a little bit about your wind tunnel plan? And it looks like you've got some data points, I think slides 14 through 16. How many runs did you do? And actually, let's go to the next one, because this one's kind of okay. So how many runs did you do?
So in the previous semester, we had written up an actual plan that we then followed. Let's see. 3 tests? Yeah, we did 3 tests for each run. So basically we did tail off, tail on, changing angle of attack, and then a blank side slip when, well, not in this case, but.
Okay, so as far as what I'm thinking about is statistical confidence in the results that you have. And if you go to the next slide, I think it's the next one. Yeah, so 4 degrees beta, is that a real point? That is my question. At that little gray point that's way down there,
that is, yes.
Is that real? And the reason I'm asking is, did you check it multiple times?
Yes, we did.
Okay, that would be great to say.
Okay.
Say how many times you went there, because what I see is you went there once, and we're not really sure if that's real or not.
We promise it was consistently terrible.
It was.
It's so important to say. That's so important. Good point. A little bit nitpicky, but you've got kind of and I know how Excel works, you've got a curve fit line kind of thing there. It shows that there's a slight local maximum just left of 2 degrees beta with the gray line. I don't know if there's really a local maximum at 1.9, but that's what your curve is showing. If that's not real, then don't fair the curve. Just show the points. Because people are gonna, so hypothetically, if I wanted to know what the beta response was at 0 alpha and 3 degrees beta, your curve is showing me that I can tell you, that I can look that out exactly. And I'm willing to bet that you don't know. Because no one knows what the actual answer is at 3 degrees beta. So if no one knows, then don't give us the opportunity to find out. Right? That's phrased a little weird, but I think you get what I'm saying.
Yes,
Okay, slides 34 through 36. May, awesome job. That was so great. I really like the way you briefed the test, like here's how we set it up. Go to the next slide. And then here are some results that we got. One of the biggest things that we really hit on with kind of Air Force tests especially, that they really emphasized the test pilots was this concept of predict, test, validate, right? So we have a prediction, we do the test, and comparing those results validates my model. Either the prediction was good or it was not. And that's exactly what you have. On the left side, you've got your prediction. On the right side, you've got your test. And I can see the two numbers and I can no, it's not valid. Right, but the fact that you came out and said that and you put this all on one slide was awesome. So for the other tests that you did, if you can say things, or if you can do this very similar, where you can show, here is our predicted stability curve, or here was our predicted takeoff distance, or whatever else. Show the prediction, show the test, say whether or not it was validated. That is the way to really give us confidence that we could either use or not use that structural model, or that model, in this case it happens to be a structural model. But that is my confidence that I can use that model for other applications. Like, hypothetically, what if I wanted to put on, I don't know, you probably got 69 pounds of weight. What if I wanted to put 50 pounds of weight? Could I use this to predict the deflection? Well, no, I wouldn't. But, or if, I said 69 pounds, what if I put 100 pounds of weight on there? Could I predict the deflection there? Again, the answer in this case is no, but you've proven to me that this is not a good model, which is an extremely important thing to be able to prove. So, predict, test, validate, do it every time, it's great. Hey, slide 66, but not really, more like slide 56. On 66, you mentioned that you did a taxi test. I wish I had known that right around here. That would have been a great thing to mention, because that's kind of implies the build-up to testing. And it shows, again, how you're, one, how you're demonstrating that it went safe, but also it's giving me confidence that you guys are kind of taking, I'll call it a scientific approach rather than a cowboy approach to testing, which is super important. I really like the narration that you had, Bjorn, on the video. That was great. One thing that I would suggest, and I know video editing is hard, I've tried to do it myself and other stuff, if you can have little bumper stickers appear, like little taglines appear, like takeoff right here, or takeoff speed equals 36 knots as it's happening. And then, so it's, it becomes this self-narrated video. And be like, flying around for basic aircraft familiarization. Cool, now I know what's happening. Rudder doublet, or whatever it is that you guys are doing as it's happening, that would be spectacular. Because what it saves you, and you didn't have, and I wish you did, was a couple slides talking about, like, actually in words, showing what the results were. There were a couple, and you got it in a few different places, but like the next slide was great, where you have specific numerical values. Throw predictions on there, and then you've got predict, test, validate, which is good. But just do that for the whole test.
So some qualitative stuff as well.
Yeah, and you can totally do it. Like, basically, I love your test cards. You should be able to have a test result for every single one of those things. And so you have a rotation speed, you probably could have a rotation distance as well, or a takeoff distance.
Yep.
So you could tabulate that. And basically every, we test some pretty big expensive stuff. It can be on the order of $15,000 a flight hour. So if you're paying $15K an hour, you better get every ounce of data out of that
Absolutely.
test.
Absolutely.
So if there's any possible thing that you can enumerate, do it.
You're
okay.
really quick, you're talking a lot about predicted stuff, and we did do a lot of that stuff. So here's the predicted speeds we had for the, that flight test, and then we did a lot of flight predictions with takeoff, landing, and we really would have loved to include it, but just with the time frame, and I understand where you're coming from.
Yeah,
I do.
I totally understand, and I really appreciate there's just so much you can't say because of time. I think probably my final, you know what, no, I'm good.
Thank you.
Thank you guys so much.
Appreciate it.
That was awesome.
Can I add a question real quick? You made me think of something. So for flight test stuff, something I've been thinking about recently with my job is off nominals. What did you guys do to prepare? Because you guys had a first in your flight test that you didn't do during your taxi test, which is landing gear retract in flight. If it retracted successfully and did not deploy successfully, what would you have done?
We did test the landing gear on the ground.
Okay.
So that was in our ground test. And the only option had it not come back down was to double land.
Okay. Would that you probably predict vehicle loss?
No, it's slide.
Okay.
I guess we didn't go into that at all. Now that you're jogging my memory, when we did the calculations for the monocoque, belly land is purely cosmetic.
Okay. Yeah, that was all I was going to ask is, just having something where it's a design solution that adds complexity like that, it can cause, something that might seem as a benefit initially, the risk of adding something
Absolutely.
might outweigh that. It seems like you guys went through that and you did your good engineering due diligence, but, and then you said that it would take off about 40 minutes of your endurance time for...
That was with the full scale, which was internal combustion.
Okay, all right.
We didn't do those calculations for the half scale,
For the subscale.
Subscale.
Okay, so, would you guys still probably be able to meet your, flight requirements in a dirty configuration instead of with the clean configuration?
We would have to do that
Okay.
calculation.
We have one more question back here.
Okay. Hello?
You mentioned that you raised the tail because of your wind tunnel data. Because your wind tunnel data on your flow viz was showing that nothing was happening at the tail. What were you looking to happen?
Airflow? Or stability, or?
Didn't you have airflow at the tail?
We did not. No,
not
that's
really.
that.
Very
That is
little.
why.
You had no airflow at the
That's
tail.
correct.
We had very little.
Yeah, it was.
How does that
My
happen?
guess is mostly
How do you
because so.
stop that flow?
From the fuselage
It
blockage.
essentially how we had it. Now we can get a look at it, because, so the cone is in the middle, right? You have it behind. My guess is that the fuselage, because it was so large, that it was blocking most of the airflow from the back. And as we were designing, right, we're looking at Raymer's, I believe it was Raymer, just as far as designing the size of control surfaces. So we scaled it to what he was suggesting, but talking to a lot of other professors and just people who have had experience with light aircraft, they suggested making it even bigger. So along with the wind tunnel results and what we saw from FlowViz, that's why. But
My question was, you raised it.
yeah,
You didn't necessarily make it bigger, you raised it, right?
We did also make it bigger.
Yeah.
It was a 25% increase.
But in raising it, what did that help you with? I mean,
Moving it up into the airflow.
Yeah.
From basically getting the control surface, the stabilizers out from behind the blockage of the fuselage.
Okay, you didn't have an engine turning up in your wind tunnel, so you got downwash off your wing. So the tail's not seeing the same angle of attack as a wing anyway. So, did you help anything?
There was
I mean, when I looked at I'm looking at your data right there, and you're telling me that the tail's not seeing anything. I disagree.
So in the strands that we used were
just laying on top of, on the trailing edge. They weren't, it wasn't because of the flow from the wind tunnel. Maybe that's why, I'm not.
So you're saying the tufts were stiff enough?
Correct.
That you couldn't
Yeah.
detect airflow over them?
Is that what you're,
I'm-
is this where this pointed
Yeah.
question is pointing?
No, I'm just asking how you made the conclusion that there was no flow at the tap.
Part of it was talking to Dr. Traub as well. He was there for part of our test and he was.
Okay, that gets to another with the other group as well. Dr. Traub is not gonna be with you next time you get asked this question. Same way with the other group. And so you're going to have to know why. Because, and that's one of the reasons when, and my guys, I won't answer some of their questions. I'm gonna say, what do you think? Because Dr. Traub's not gonna be with you, or Dr. Morris is not gonna be with you next time you get asked this question. You need to know why. If you just say, well, we changed it because Dr. Traub said so, that's not gonna help you in 2 months or whatever it is when you get where you're going. You need to know why. End of my point. You guys did a great job. Both teams did a great job.